Okay, so we want to start pulling everything together now. And so here, and it's a little messy, I'm sorry, but here I've listed 4 different series, as well as the 4 different tests. I mean, we also have telescoping series. That's kind of off in its own world. But I've listed 4 of the main tests that we've discussed in this chapter so far. So nth term test for divergence, let me stress, geometric series, p-series, and integral test. The plan, or the giveaway that I gave in the instructions, is that you're going to need to use each one of these tests once with these 4 series. So let's look through them one by one. Or, we don't have to go in order. You're going to want to learn to recognize geometric series and p-series quickly to save yourself some time. So if you're scanning all of these series, let's go with geometric. For which one's geometric? The thing to look for a geometric series is constant base raised to the n. So n in the exponent. We have an n in the exponent here, but not in the denominator. This is not an exponential expression. To call something a geometric series, it has to be in this form, a times r to the n, where the a and the r are constants. And while we're talking about it, p-series is another one where people want to call it a p-series when it's not exactly in the correct form. So for a p-series, it's got to be 1 over n raised to the constant p for your exponent. So for scanning first, because those are the quickest tests to use, so it's good to be on the lookout for those, for when we can use each of those tests. C, notice you have a constant base n in the exponent. So the series that I wrote there as series C could be written in the form 1 over 5 to the n. So sum from 0 to infinity. So this is a geometric series with a common ratio r equal to 1/5. The r is always the base of the exponent. This a r to the n. R is the base that's raised to the n power. So in this case, r is 1/5. For a geometric series, they converge when the absolute value of r is strictly less than 1, which it is in this case. And so this series converges. So let's label this guy over here. So this one converges. Now, looking for a p-series. So constant base, n for the base raised to a power, a constant exponent. So this one might tempt you, but with natural log of n as your base, that's not going to work. For a p-series, your base has to be just n. Natural log of n is not, that's not a p-series. So the one that's a p-series is d here, because d can be written, the cube root can be expressed as the 1/3 power. And so this one is 1 over n to the 1/3. This is a p-series with p equal to 1/3, which for a p-series, when p is strictly less than 1, or in fact less than or equal to 1, the series diverges. So d here diverges by the p-series test. And let me label each of these because it's important in your homework and on your exams that you state not only does it converge or diverge, but how you know. So this is a geometric series. That's how I know for C. Okay, so now we just need to deal with A and B. And we have used geometric series test. We've used the p-series test. So we're down to nth term test and integral test. The integral test, nth term test is the one I wanted to talk about, only applies if the limit of the terms is not approaching 0. So as n approaches infinity, note that the terms here are approaching 0. So nth term test does not apply. So if I'm going to apply nth term test to one of these, and you do want to apply nth term test, this is another one you want to be on the lookout for, along with geometric series and p-series, because these are all very quick and easy tests to apply. So you don't really want to do integral tests. I mean, you'd have to turn it into an improper integral. You have to evaluate the integral. You have to jump through a lot more hoops to determine convergence or divergence with the integral test. If you can apply one of these first three instead, then that's what you should do. So with integral a here, if we check the limit as n approaches infinity of e to the n over 5n plus 1, this limit has the form infinity over infinity, which is indeterminate. But if we apply L'Hopital's rule, the derivative of the top is e to the n, the derivative of the bottom is just 5, and so as n approaches infinity, this is increasing without bound. This is approaching infinity, which if you get anything for your limit other than equals 0, so if you get like oscillating behavior, limit doesn't exist, or if it's approaching infinity or negative infinity, any of those scenarios, nth term test can tell you that the series diverges. Only time nth term test doesn't work is if the limit equals 0, which is usually the case. I mean, notice all three of these series, if we take the limit as n approaches infinity, this is approaching 0, this is approaching 0, this is approaching 0. They all have that form 1 over infinity, so they're going to 0. This is the only guy that doesn't. And so A here diverges by the nth term test. Okay. So that leaves us with B, and it leaves us with one test to apply, the integral test. So that's got to be the test that we use. It's a good idea to try this one B before you watch me solve it, because I'm going to try to do it real quickly to keep this video from being too long. So you might want to pause right now and consider the integral from 1 to infinity of 1 over x times natural log of x to the 5/4. Determine if that improper integral converges or diverges. By the way, so I'm jumping the part where I write positive continuous decreasing. You should always verify that before you apply the integral test. I'm going to just real quick, verbally go through this. So if n is 2 or bigger, this expression is certainly positive. It's continuous because we don't have to worry about the denominator being 0. N is 2 or bigger. We don't have to worry about encountering that vertical asymptote in the natural log graph because that happens when n equals 0, which is not part of this sum. So it is continuous and it is positive. Decreasing, sure. So if your denominator is increasing, numerator is fixed, then the fraction is getting smaller and smaller and smaller. So this is a decreasing expression. Okay, so we can apply the integral test. In order to integrate this, you would use the substitution. I used it in the previous example. U equals natural log of x. And if you do that, then du is 1 over x dx. So this 1 over x dx is du. And so this integral here has the form 1 over u to the 5/4, 5 over 4 times du. So that's the integral of u to the negative 5/4 times du. And we know we're using integral test. I don't really need to keep all of this anymore. Let me give myself some room here. So if you apply power rule for antiderivatives, this will be u to the, let's see, if you add 1 to that, so add 4 over 4, you're left with negative 1 over 4 over negative 1 over 4, if we want to write it that way. Bring this up, multiply by the reciprocal, so that's negative 4 over u to the positive 1/4. Right, bring this up, and then this is a negative exponent, so that goes down. They kind of trade places there. Okay, so let me come back to the improper integral here. So this is equal to the limits as t approaches infinity of this antiderivative, which is negative 4 over u, which is ln of x, to the 1/4. Okay, evaluated from 1 to t. Now something that I haven't been doing that's been kind of driving me crazy, constants like this, -4, we could pull that out in front of the limit if we want to. And I want to. I just haven't been doing it to minimize the steps that I'm showing you guys. But now I'm going to go ahead and... So -1/4 is a constant coefficient. I can put that out. Limit as t approaches infinity, then, of 1 over natural log of x to the 1/4, which if you want, you could write that as the 4th root of natural log of x. Maybe you don't want to, but you can if you want to. Oh, and this should be t now. Minus 1 over, oopsie. Yep, I finally noticed. If x equals 1, then you're dividing by 0 here. Natural log of 1 is 0. This should be 2 to infinity, like it says here. So this should be a 2 here. And so this will be 2 times, whoopsie. Plug in 2 here. This will be the 4th root of natural log of 2, which is some finite number. You can plug it into a calculator, some irrational number. But the point is, this is a number here. Always with integral tests, what we're worried about is where we plugged in t, and t is approaching infinity. Is this growing without bound? So as t approaches infinity, this denominator is increasing very, very slowly, because we took an already slowly increasing function, natural log of t, and then we took the 4th root of it, so we're flattening it even more. So flattened curves, are big in the everyday, conversations today. Here's something we've really flattened, this 4th root of natural log of t. But, okay, I digress. It is increasing, just very, very slowly. So you've got something of the form 1 over infinity. That denominator is increasing without bound. And so this limit then, number over infinity, that's going to 0. And so overall, what you've got... Now, let me pause before I bother with it. We don't care what the actual number is here. At this point, we know it's not increasing without bound. It's not going to infinity. Oh, so we know it converges. We don't care what the integral converges to. If the integral converges, then the associated series here converges. So this series, at this point, we know it converges by the integral test. However, just to show you guys how you work through it, I'd like to get a complete answer here. So our final answer, as far as if we were evaluating the integral converges to -4 times 0 minus 1 over the 4th root. Yeah, it's too ugly to even mess with. 4th root of natural log of 2. So negative times a negative, positive 4 over the 4th root of natural log of 2 for what the integral converges to. But again, I'm fine with it if you guys stop here, because at this point it's a finite number. So the integral converges, and so the series converges.